Okay, we're continuing with chapter 11, which is on infinite sequences and series. In this video, we're going to go through section 11.2, which is titled Series. But again, as I've mentioned in previous videos, we're not being introduced to the concept of a sequence or a series in this chapter in calculus. That was done in algebra. And that's why, if you're following along in the playlist, I've included a bunch of the videos from the algebra playlist that go into detail on what is a sequence, what is a series, some of the fundamentals. In calculus, what we're focusing on is the idea of an infinite sequence or series. And in section 11.1, we looked at infinite sequences. And so, as you can imagine, in section 11.2, we're going to focus on the idea of an infinite series. Okay, and so remember a sequence, you can write it as like A sub n. This symbolizes a sequence. And some sequences, not all, but some, you're able to come up with a sequence formula. It's a function of n, some expression of n, where n represents the nth term of the sequence. So the vast majority of the sequences that we deal with in this textbook and example problems and even in practice, they're going to have a starting point, usually like they're starting at 1 or 0, but they don't have to. And so the idea of the nth term is that, so if it's starting at 0 or 1, then maybe you want to find out what's the term number 5. So you plug in n is equal to 5, or term number 50. You plug in n is equal to 50 into that function of n, the formula for the nth term. You can also write a formula for a sequence recursively where it's like, it's still a function of n, but it's like the nth term is a function of previous terms. That's like recursive formula, but that's still the idea of a formula for a sequence. Okay, but what a series is that you're summing the terms of a sequence. Now, technically, a series doesn't mean that you have to sum every single term of a sequence. You could have like a partial sum, where maybe you sum the first 500 terms of a sequence, or maybe you sum from term 10 to term 70, and that's still the idea of a series. You're summing terms of a sequence. And the way you write a series is you put a summation symbol, and then you take the sequence and you're summing the sequence, but instead of putting a sub n, you put sub I. Now, I believe this symbol doesn't mean that you have to have a sequence formula. I think this is just like the general symbol for any sequence. But you could think about it like you would still take the sequence formula, if you had a sequence formula, and replace the n with an I. And you do this because the idea is you're summing from I is equal to the starting point, which, usually for a sequence is going to be 0 or 1. Let's say it's 1. But again, doesn't have to be at the first term, starting with the first term of the sequence. You could start anywhere at 50. But most commonly, you start at the first term of the sequence, and then you go to n, the nth term. So that's whatever you want. It could be a partial sum where n is equal to 50 or 1,000, or it could be what we're studying in this section, an infinite sum, where you're doing this. Okay, so this is what we're studying. All right, so it says, what do we mean when we express a number as an infinite decimal? For instance, what does it mean to write? And so they write out pi with a bunch of terms. The convention behind our decimal notation is that any number can be written as an infinite sum. Here it means that, so yeah, what does this mean? 3 plus 1/10 plus 4 hundredths plus 1,000th plus 5 10,000ths. And the dots indicate that the sum continues forever. And the more terms we add, the closer we get to the actual value of pi. In general, if we try to add the terms of an infinite sequence, we get an expression of the form. So yeah, you can write it this way. The first term plus the second term plus the third term plus ... the nth term ... Where, again, notice what it said. We're adding the terms of an infinite sequence. So don't forget that a sequence is intimately related to a series. Don't forget that. With a series, you're summing the terms of a sequence. So every series has a corresponding sequence. every series is like married to a sequence, right? Sometimes you see this a sub I, and you're so used to thinking of a sequence as an a sub n that, at least this happened for me, that you kind of forget that no, these are both sequences. They're the same sequence. You just replace the n with an I for the summation. Okay, and so if we sum the terms of all of the terms of an infinite sequence, in general, that's what a series is going to be. You're summing all of the terms of a sequence. That's kind of the most common scenario. You're summing all the terms of a sequence. So if you're summing the terms of an infinite sequence, that's called an infinite series. It says or just series. And yeah, the terminology can be a little confusing. You know, they're going to refer, we're going to just use the term series when we're referring to an infinite series. But what I've gathered, the best way to look at it is you've got sequences, which are list of numbers, list of elements. You can have finite sequences where you have a finite number of elements in a sequence, or you can have infinite sequences, which is where you have an infinite number of terms in a sequence. Okay, a series is where you're summing the terms of a sequence. If you're summing the terms of a finite sequence, you can call that a finite series. If you're summing the terms of an infinite sequence, then that's called an infinite series. But you can just use the general term sequence or series when kind of casually referring to any sequence or series, whether it's infinite or finite. So I could tell you, hey, I got a series I want to show you. And I give you the series, and then you look at it and say, oh, okay, this is an infinite series. This is a finite series. I don't have to specify each time that I can just, series is kind of an all-encompassing term for any series, and same with sequence. Okay, now we're also going to see that if you have a sequence, whether it be an infinite sequence or a finite sequence, but you're summing just a portion of the terms, then that's called a partial sum. That's another term. All right, so an infinite series is just when the n here goes to infinity. Or they say the sum of just the a sub n, but I don't know how do you know that a sub n is infinite, is an infinite sequence? I guess because it has the n in it. So you see what they're saying here. This is called an infinite series and is denoted by, for short, by the symbol this, the sum from I is equal to 1 to infinity of a sub n, or just the sum of a sub n. And I guess the reason they're referring to this as an infinite series is because if you say a sub n, then, I guess this is kind of implying that n can be anything. Right? If you have a formula for a sequence with just like as a function of n, then technically n can go to infinity, right? N is whatever you want. So, okay. Does it make sense to talk about the sum of infinitely many terms? Yeah, this is kind of weird, right? Does it make sense to say we're having an infinite sum? Wouldn't any infinite sum just kind of balloon to infinity every time? Is it kind of, what's the purpose of this? It would be impossible to find a finite sum for the series 1 plus 2 plus 3 plus 4 plus 5. And so you can see this is you're summing an arithmetic series where each term is separated by 1, right? It's 1 plus 2 plus 3. Because if we start adding the terms, we get cumulative sums. 1, 3, 6, 10, 15, 21. And after the nth term, we get n times n plus 1 divided by 2. Okay, and where did they get this n times n plus 1 divided by 2? Well, this comes from when you determine the formula, the summation formula. This comes when you determine the arithmetic series formula, the partial sum formula. So if you wanted to find the sum of the first 10 terms of this arithmetic series, then you plug in n is equal to 10 and you get the sum of the first 10 terms. And in algebra, we talked about what's the general formula for any arithmetic sequence, the sum formula. So we called that S sub n is n times a1 plus a sub n divided by 2. And we saw how to derive this. Again, if you're summing the sum of the first n terms of an arithmetic sequence, that's exactly what this is, right? You can have different types of arithmetic sequences they can have different starting points and different common differences, right? This is a common difference of 1. But the formula for the sum of the first n terms of any arithmetic sequence is given by this formula. And we saw in algebra how to derive this formula. And so that's in the videos just before this. I included those videos from the algebra playlist. So hopefully you watched that. And one way you can look at this formula is what we talked about in those videos was that, so, okay, the sum of the first term of this sequence is 1. The sum of the first 2 terms is 3. The sum of the first 3 terms is 6. And that's what they're showing here. And you get another sequence, right? And that sequence is called S sub n. S sub n is intimately tied to an A sub n. And so we worked example problems where in algebra, and those are included in this playlist, where we're given a sequence and we try and derive what the sequence formula is if it has one. And so you can imagine that's really valuable, that you can take any sequence and you could write out the first like 5 or 6 terms of its S sub n formula, and then do that process of trying to analyze the S sub n sequence, the first 5 or 6 terms, and come up with a summation formula in S sub n. And when it comes to arithmetic sequences, where we were actually able to come up with a general formula, where we were able to succeed in doing that, which is not always the case. That's actually hard to do, to actually come up with an S sub n formula. Okay, and you can see if we compare these two formulas, A sub 1 is 1. A sub n is just n in this case, right? It's very simple. It's just n. So you have n times n plus 1 divided by 2. Okay, but as they mentioned, when it comes to an arithmetic sequence, it's always just when you think about the infinite sum, so when you think about taking the limit of this formula as n goes to infinity, with an arithmetic sequence, it's just going to go to infinity, right? As you come to the S sub n sequence, as n goes to infinity, this is, for any arithmetic sequence, it's always going to go to infinity, assuming you're starting at a certain start point, okay? But now they say, what if we add the terms of this? What if we try to evaluate this series? So we're adding the terms of a sequence, right? The sequence is 1/2, 1/4, 1/8, 1/16, and so this is the A sub n for the sequence, right? It's confusing. We're adding the terms of the sequence, but then what they do is they say, okay, the sum sequence, the S sub n for this that corresponds to this sequence, starts at 1/2, and then 1/4 plus 1/2 is 3/4. 1/8 plus 1/4 plus 1/2 is 7/8, and they get this new sequence that they label S sub n. Anytime you see an S sub n, either in formula form or like written out like this, it has a corresponding A sub n that you're adding the terms of that A sub n. Okay, and so with this is actually a geometric sequence that we're adding. But if we look, going from n is equal to 1 to 25, it looks like we're approaching 1 from below. And so this is more interesting, right? This is not like the arithmetic series. This looks like it has more potential meaning to it, as far as it's actually converging to something. If it was truly converging, like going to 1, then we'd put in n is equal to 5 billion, and we still should get something that's below 1, but not at 1. And so they say, so it seems reasonable to say that the sum of this infinite series is 1. If we plugged in 5 billion and got something below 1, 0.999, a lot of nines, but not 1, then it seems reasonable to say that the sum of this infinite series is 1. And then we write the sum from n is equal to 1 to infinity of the sequence formula, this is a geometric sequence, is equal to 1. Which is really cool, right? And the idea of an infinite sum, a true infinite sum, truly infinite, right? And what does that mean? Well, if we plugged in 5 billion, and is equal to 5 billion, it's not equal to 1. The sum is not equal to 1. It's very close. It's not equal to 1. It's only if you take the limit as n goes to infinity. If you plugged in, only God could plug in whatever infinity means, and then in that case, if you did that, it would be equal to 1. If you summed an infinite number of terms, it would be equal to 1. Okay, and so here it's saying we use a similar idea to determine whether or not a general series has a sum and this is what I was talking about up here with the S sub n, we consider the partial sums, S with n is equal to 1, S with n is equal to 2. Those are partial sums. You're not summing the entire sequence. You're summing a portion of it. S sub 3, S sub 4, and then you get S sub n, right? An S sub n formula. If you can find an S sub n formula, that's really nice. But it's not that easy to do that. But if you can get an S sub n formula, and you know, what you can imagine is you can't just, you could write out the first 5 terms of a sequence sum, and let's say you find a formula that works for those 5 terms, an S sub n formula, but you still need to prove that that formula is true for all n's. And when it came to arithmetic and geometric partial sum formulas, we what you saw in the previous videos, the algebra videos, was how we could use some clever techniques to find those formulas. But with more general situations where, you know, it's not easy to use these clever techniques like you could do with arithmetic and geometric, what you can do is that's what induction can be used for. Mathematical induction. You're proving the truth of a statement over a set of positive integers, right? So you would write out the first 5 or 6 terms of a S sub n for a sequence, get a formula that you know is true for those first 5 or 6 terms, and then use mathematical induction to prove that that formula is true for all positive integers. All right, so these partial sums form a new sequence, S sub n, which may or may not have a limit. And that's what's nice. If you can actually get the S sub n and you know it's correct, well, then you just take the limit as n goes to infinity of the S sub n. And then you're done. I mean, it's either, if it converges to a number, then that's the sum. That's the infinite sum. If it diverges to infinity or whatever, then that's what the sum is. Okay, but this S sub n may or may not have a limit. If the limit as n approaches infinity of S sub n exists as a finite number, then, as in the preceding example, we call it the sum of the infinite series. Okay, and with that, we come to this definition here. And this is the main definition of this section, because it's in this definition where it's going to define what a series is and what it means for a series to be convergent or divergent, right? That's the main purpose of these first 2 sections. We're studying infinite sequences and series. Well, we studied what it meant in the previous section. We studied what it meant for a sequence to be convergent or divergent, and then how to analyze a sequence to see if it's convergent or divergent, and then if it's convergent, what it converges to, or if it's divergent, what are some of the specifics of the divergence, if we can give those. Okay, so what does it mean for a series to be convergent or divergent? So if we're given a series, and here's kind of the definition of a series, right? But actually, this is an infinite series, more specifically an infinite series, but this is, when it comes to studying convergence or divergence of series, we're always going to be dealing with an infinite series. You can't think about the idea of, if a series with 50 terms, does it converge or diverge? That doesn't make any sense. We're always thinking about, when it comes to convergence and divergence of series, we're thinking about going off to infinity. The vast majority of the time, the series starts at a certain point, and so we're thinking about what happens as the series goes off to infinity. So given an infinite series, so that would be what? The summation, and they put n is equal to 1 to infinity in a sub n. And so in this situation, they could just put a sub n instead of a sub I, because if you had this going from like I is equal to 1 to n, and then you're taking the limit as n goes to infinity, it just depends on how you want to write it. Okay, but you're summing the terms of this sequence a sub n we're summing from the first term to infinity, right? So this infinite series, and then if we let S sub n denote its nth partial sum, so now we change to this formula for the summation a sub I, so we can go from I is equal to 1 to n. In that case, we can say S sub n, and they put this because this is a sequence, right? S sub n, just like a sub n, this you can write as a sequence. So if you said n is equal to 3, then S sub 3 is the sum of the first 3 terms. That's the third element of the S sub n sequence. Okay, if the sequence S sub n, and I know this is confusing. We're switching between sequence and series, and okay, if the sequence S of n is convergent and the limit as n approaches infinity of S of n is equal to S exists as a real number. And so we'll have to see as we go, but I was under the impression that if S of n is convergent, then the limit of the S of n sequence exists. It's kind of like convergence of any sequence. If any sequence is convergent, then that sequence converges to L. But they're saying it like if the sequence is convergent and also at the same time the limit as n approaches infinity of S of n is equal to S exists as a real number. So I have to come back to this potentially later and see if maybe they mean what they mean by this. Like there's kind of like two conditions here. But I'm looking right now. I'm looking back at the definition of the limit of a sequence and sequence convergence and divergence, and it says a sequence has the limit L. So like L would be a number. It has the limit L if the limit as n approaches infinity of a sub n is equal to L, and that's what they're saying here. The limit as n approaches infinity of S sub n is equal to S. So if that limit exists, we say that the sequence converges. Otherwise, we say that the sequence diverges. So I guess those two definitions are pretty similar. Yeah, I mean, the idea is if you have the S sub n sequence, and then you take the limit as n approaches infinity of the S sub n formula, and if that exists as an actual number, then the corresponding series, right, because every S sub n is tied to some a sub n that you're summing the terms of the a sub n, and there's the sum of the a sub n. It's called convergent. And you can write the convergence of the series. Here's the sum of the a sub n terms, or you can write it like this, and it's equal to S. So a convergent series is going to be equal to a value. Okay, if you have any series that's convergent. So let's just make sure we understand what they're saying here. If you have a series, okay, so we're thinking the series starts at a certain point, n is equal to 1 or 0 or wherever. It starts at a certain point, and then it's not defined to stop anywhere. It can, hypothetically, you could plug in any n you want that's greater than or equal to 1 or 0 or whatever. Okay, if you think about summing the terms of that sequence from the standpoint of you sum an infinite number of terms of that sequence, because again, the domain is any n can go to infinity. If you think about the idea of summing an infinite number of terms of that sequence, and that ends up being an actual real number, a single number, then that series is said to converge. Now, the idea of summing an infinite number of terms, that's kind of hard to say. What do we mean by that? Well, one way to describe that is if you have an S sub n, which is you could look at as a formula, as a function of n, or you can look at S sub n as a sequence, either one, right? Because that's what an a sub n, you can look at an a sub n as a formula or like a list of numbers. So same thing with an S sub n, and S sub n just represents the nth partial sum of the sequence, starting, implied to start at the first term. Then if S sub n, the sequence S sub n is convergent, if S sub n is convergent, I couldn't start off by saying if the sum of the a sub n's is convergent, because we don't know what that means. But we can think about, if we think about this S sub n as a sequence, which we can, then we can think about S sub n being convergent or not, because we just went through a whole section with example problems on analyzing the convergence of a sequence, right? So if the S sub n that corresponds to the sum of the a sub n's is convergent, and then also at the same time, you should have like an S sub n formula, and you're able to show that if you taking the limit as n approaches infinity of that S sub n, that's equivalent to the idea of summing an infinite number of terms of the a sub n sequence, and you can show that actually this is kind of confusing to me. To me, if it's both of these have to be true at the same time. Like you can't say it's convergent and then not have this take place, right? If it's convergent, then that means this is true. If this is true, that means it's convergent. So it's not like I don't see how you could decide that S sub n is convergent and then discover that this is not true or something. I guess maybe what they're saying is you have to be able to prove this as well. So if you can't come up with a S sub n formula, then you couldn't show this explicitly, and so you wouldn't be able to say S sub n is convergent without some other means. So you have an S sub n, and you can come up with a formula for the S sub n. Then you could, and with that formula as a function of n, you could take the limit and show that it's an actual number, which means that, what does that mean? That means that the sequence is convergent, right? That's what it means for the sequence to be convergent. That the formula for the sequence, if you can come up with one, as n goes to infinity, it equals to an actual number. Not, it doesn't go off to infinity or negative infinity or oscillate or whatever. Now, if you can't come up with a formula, then we didn't talk about how to look at it that way. Okay, but we have a sequence, a S sub n sequence formula. We determine if it's convergent by finding its limit as, n goes to infinity. If that limit exists, which means that the S sub n is convergent, then that means that the corresponding series of the S sub n is convergent. Then we can say that kind of odd thing to say, that an infinite sum is equal to an actual number. So that's important to understand as well. If we're saying a series is convergent, then the idea of an infinite sum, that's what we're defining to be an infinite sum, is whatever it converges to. So just to stress how, this is pretty interesting. If we come back here, okay, the idea is for the series based on the sequence 1 over 2 to the n. Okay, if you summed 100 trillion terms of the first 100 trillion terms of this sequence, you're going to be very close to 1, but you're not going to be at 1. You're going to be very close. It's only when you kind of quote unquote hypothetically think about summing an infinite number of terms, then it's exactly equal to 1. Okay. If the sequence S sub n is divergent, then the series is called divergent. Okay. So as it says here in this previous example, that in that example where they found, so okay, they were given the S sub n formula, and then with that you could just find the limit of this formula. If it goes to a value, then you know that the actual sum of the sequence, the series, is convergent, and the sum is equal to, it was 2/3. And it says, in this example, we were given an expression for the sum of the first n terms, but it's usually not easy to find such an expression. In example 2, however, we look at a famous series for which we can find an explicit formula for S sub n, and this is the geometric series. In this section, we don't go over the arithmetic series because it's divergent. But the geometric series is convergent, and we're not going to get too deep into this because in one of the algebra videos that's included in the playlist, we formulate the geometric series. We go through this entire proof here, and what you get is that you get the S sub n, the nth partial sum of a geometric series. You could get the sum of the first 50 terms, the sum of the first 100 terms, and all it is you've got. So if we come here, a geometric sequence is represented by this formula: a times r to the n minus 1. That's one of the ways you can represent it. Okay, and so the nth partial sum for this form of a geometric sequence, the nth partial sum of the corresponding geometric series, assuming we're always starting at the first term and then summing the whatever n we put in, is the a coefficient, and then the r is the base, and then that's it, and then there's the n. All right, now if you take the limit as n goes to infinity of the S sub n, in some cases it converges, and it depends on what the r is. What you can think about, the r needs to be between -1 and 1, and that was when, if you can think about this, is kind of, that's like, so that's what we saw for the convergence of a geometric sequence. They didn't call it a geometric sequence in the previous section, but it was the same idea of a base to a integer power, where the integer power is positive. That sequence was convergent when r was between -1 and 1. It was also convergent when r was equal to 1, but it didn't converge when r was between 1 and -1. It converged to 0. The sequence. When r was equal to 1, it converged to 1, and then when r was less than or equal to 1, it was like an oscillating divergence. And then when r was greater than 1, it was a divergence, but it diverged to infinity. Okay, now, but they're saying here, though, that the corresponding S sub n, is only convergent when r is between -1 and 1. When r is equal to 1, they're saying it's not convergent. The S sub n. So the series, the corresponding geometric series that corresponds to the geometric sequence. A geometric sequence that's turned into a series is only convergent when r is between 1 and -1. And even though the sequence converges when r is equal to 1, the series doesn't when r is equal to 1. Okay, and so they summarize this here, the geometric series written, and so you can write geometric series with different forms, but in general, any geometric series is going to be convergent if the common ratio, the base, the absolute value of it is less than 1. And its sum is equal to this, but if you had a different geometric series formula, like you could put a times, there's different ways you can write it, then you'd have to, you'd get a different, it'd be slightly different than this, right? The S sub n is going to be a little bit different depending on the geometric formula you start with, the sequence formula. But you just use the same method that they just showed here and that we go through in that algebra video with whatever formula, sequence formula, geometric sequence formula you have. This method will work to get the corresponding S sub n and the corresponding actual. This is the sum of the infinite series here. This isn't the S sub n. This is the actual just S. They're calling this like the actual infinite sum value with what the S sub n converges to. Okay, here they give a simple example. We're going to work a bunch of examples. Let's take a look at some of these examples. So, all right, here it says, is this series convergent or divergent? And what you want to do is simplify this to put it into the form they gave above in equation or definition 4. So they use the properties of exponents to simplify it to this. And that's in the exact form above, of the definition above. And so you can see 4/3 is greater than 1, so this diverges. This series, right? This is a series with a corresponding sequence formula. Okay, here, and so again, we're going to skip some examples, but we're going to work all of these types of examples in the upcoming videos, the example problem videos. So, but I just want to go over some of these examples. Write the number, so 2.317 with the 1 and 7 repeating, 2.3171717 as a ratio of integers. And so, yeah, remember, we can write a rational number, we can write as a ratio of integers, any rational number. And infinitely repeating decimals were included with rational numbers. If you remember in pre-algebra, an infinitely repeating decimal, if it was repeating with that like a repeating pattern, then you can write it as a ratio of integers. But like pi doesn't have a pattern. You can't write out 3.14 and then like the next 10 terms and then put a bar over those 10 terms and it's repeating to infinity. But if you have a repeating decimal, you can write it as a ratio of integers. So how do we do that? Okay, well, what they do is they say that this number is equal to, so 2.3 plus, and then 17 over, it would be 10 to the third, right? Because the 7, this is the thousandth place, plus then 17 over 10 to the fifth, plus 17 over 10 to the seventh, all the way out to infinity. After the first term, we have a geometric series. Yeah, so after 2.3, we have a geometric series with a is equal to 17 over 10 cubed, and r is equal to 1 over 10 squared. So yeah, this is the first term is 17 over 10 cubed, and then we're multiplying this. The next term is multiplied by 1 over 10 squared. The next term is multiplied by 1 over 10 squared, etc. So any repeating decimal is going to have a common multiplier like this. It's going to be 1 over 10 to some power. If it's 2, if the bar is over, it depends on how many digits the bar is over. If it's over 3 digits, it's going to be 1 over 10 cubed. If it's over 1 digit, it's going to be 1 over 10. Okay, and so this is, you can write this as it's what you have is 2.3 plus an infinite sum, right? An infinite sum of a geometric series where the common ratio is between the absolute value of the common ratio is between 1 and -1. And we just saw, if we come back, if you write the geometric series with this form, the actual literal value, exact value of the infinite sum is this: first term over 1 minus the common ratio. And that's what they put here, and so you get 23 over 10 plus the infinite sum is 17 over 990, and so there you go. That's exactly correct. Exact. Okay, let's skip example 7. Example 8. Show that this series is convergent and find its sum. All right, so they write out the first few terms, and then they make they write out the first few terms of the sum, I think. Oh no, what do they do? Okay, yeah, they write out. This is not the s sub n. This is just they're summing. This is one of the terms that's being summed. This is the a sub n formula. Okay, now what they say is, let's do partial fraction decomposition on the a sub n, and so we can write the sum like this. But now they've replaced n with I because they're using the summation. I is equal to 1 to n. Okay, now this ends up being a case where there's some cases of sequences when you turn them into sums where it ends up like you can solve for the infinite sum because you can use some tricks. That's what we did. That's what you do with arithmetic sequences. That's what you do with geometric sequences. Well, arithmetic sequences the infinite sum doesn't converge, but you can get the s sub n. If you can get the s sub n, then you're home free, right? But what happens here is, so they split it up like this, and then when you write out the sum this way, you can see these terms cancel, and you get the s sub n formula. It's 1 minus 1 over n plus 1. You get the s sub n formula. And you don't need to, you might say, well, okay, don't we need to prove that this is the correct formula over all positive integers? I mean, you could do induction to prove it, but no, you don't have to, because this is different. When I was talking about that, what I was saying was you have the sequence and you write out the first like 5 or 6 terms of the partial sum, and then you analyze those terms and you see a pattern, and then you find a corresponding formula for that pattern in formula. But that's only true for the first 5 or 6 terms. Here, this is the exact definition of the s sub n. Exact, right? They do the first few terms of the sequence plus ... all the way to the nth term. This isn't the infinite sum. This is the s sub n. So that's why we're not putting plus ... This isn't the infinite sum. This is just the s sub n. This is 100% the s sub n. Now we can't do anything with this because it's a big jumble. It's a big mess, but this is s sub n for sure. Okay, you do the partial fraction decomposition. You write the s sub n this way, but they had it with the. Now we're looking at it from the I perspective, and then this is the entire s sub n, right? And it simplifies to this. We made the simplification all the way to the nth term. It simplifies to this. So this is the s sub n. So you got the s sub n. Now just take the limit. The s sub n converges. It goes to 1. So this sum is equal to 1. The infinite sum is equal to 1 because we took the limit as n approaches infinity of the s sub n. Okay, so here they say show that the harmonic series is divergent. So this is the harmonic series. The sum of the sequence is 1 over n, and we're saying it's starting at 1, and you can imagine this would get a little confusing if you started at 0, let's say. Then you might have a slightly different, even if you started at 0, like I think in Europe they like to start sequences at 0, then you might have slightly different values depending on what it is, but it's all the same idea. Okay, I'm just trying to make you aware of see where you're starting. In this textbook, we're always, for the most part, starting at 1. But, also included in the previous videos from the algebra playlist are the summation properties and working with summations. We go through all that as well. And so in those videos, we talk about, if you want to switch the starting point, how you deal with that. but just be aware of the starting point. Okay, so it says for this particular series, it's convenient to consider the partial sums S2, S4, S6, S8, S16, S32. So that's like 2 to the first, 2 to the second, 2 to the third, and show that they become large. So S2 is 1 plus 1/2. S4 is 1 plus 1/2 plus 1/3 plus 1/4 is greater than 1 plus 1/2 plus 1/4 plus 1/4. Yeah, because you made 1/4 is smaller than 1/3. 1 plus 2 over 2. S8, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/6 plus 1/7 plus 1/8. And then they change this to, both of these are 1/4. And all of these are 1/8. And that ends up coming to 1 plus 3/2. And so this pattern is S of 2 to the n is always greater than 1 plus n over 2. And it shows that as S of 2 to the n goes to infinity, n goes to infinity. And so the sequence S of n is divergent. It's just proving that it's divergent. It's just a method of proving for 100% that this is a divergent series. Therefore, the harmonic series diverges. All right. Theorem. If the series, this infinite series, any infinite series, so here's your sequence that's been put into an infinite series. If the series is convergent, meaning the infinite sum exists and it's a number, then it must be the case that the limit as n approaches infinity of a sub n is equal to 0, that the corresponding sequence converges and it converges to 0. Okay, and so this makes sense that when we looked at the geometric series, we saw that the series converged when r was between -1 and 1, and we know that the corresponding geometric sequence converges to 0 in those cases, but the series was divergent when r was equal to 1, even though that we know that the corresponding sequence is still convergent. It's still convergent, but it converges to 1. So that checks out with this theorem. The corresponding sequence, the sequence that corresponds to the series, needs to also converge, and furthermore, it must converge to 0. Okay, with any series, we associate two sequences: the sequence of the S of n of its partial sums, and the sequence A sub n of its terms. If this is like the infinite sum of the A sub n's is convergent, then the limit of the sequence is definitely convergent, right? Oh, yeah, because these mean the same thing. If this is convergent, then the sequence S sub n is convergent 100%. And as Theorem 6 asserts, the limit of the corresponding sequence is 0. Yeah, that's what we just said. Note that the converse of Theorem 6 is not true in general. If the limit as n approaches infinity of A sub n is equal to 0, we can't conclude that the corresponding series is going to be convergent. That's convergence. That's important to note. Just because you find out that a sequence is convergent and converges to 0 doesn't mean that when you put it into that sequence into a series, that series is going to be convergent. Observe that for the harmonic series that we just did. That's one of the main reasons they wanted to show it. That the sequence of the harmonic series is convergent and it converges to 0, right? 1 over n, the sequence 1 over n converges and it converges to 0, but we just showed that the corresponding series is divergent. All right, so now they give a test for divergence. So that's what we're going to be doing in the example problem. Is we're going to be given a sequence or a series, and we want to determine, is it convergent or is it divergent? And if it's convergent, what does it converge to? What is the infinite sum? That's what we want to do. So here's one way we can test for divergence. If the limit of the sequence A sub n does not exist or is equal to 0, then the corresponding series is divergent, okay? So it might sound like we're talking in circles here, but we're not. We just said that if the limit of the sequence is convergent and it converges to 0, then that does not mean that the corresponding series is convergent. However, we can say for sure that if a sequence is divergent, so it does not exist, like it's infinity or whatever, or if it's convergent but it doesn't converge to zero, then we can say for sure that the corresponding series is divergent. That's a test for divergence. And the reason this is true is because it's like they say here, the test for divergent follows from theorem 6. If the series is not divergent, then it's convergent. Yeah, it's kind of interesting. So this is kind of mathy stuff, but there's only two possibilities. The series is either convergent or divergent. So if the sequence if the sequence doesn't converge to zero, then that's the only other options are that it's going to be divergent or converge to something that's not zero. But this theorem says that the only way for the series to be convergent is that this has to be the case. So this test for divergence is saying that, okay, if that's not the case, then it has to be divergent. That's the only other option. That's kind of mathy stuff, but it's interesting. Okay, so here they work an example. Here's the sequence formula, and they take the limit, and it's not equal to zero, so you know that this series diverges. Okay, note, if we find that the limit as n approaches infinity of a sub n is not equal to zero, we know that the corresponding series is divergent. If we find that the limit as n approaches infinity of the sequence is equal to zero, we know nothing about the convergence or divergence. Okay, yeah, so if we find that the limit, this is interesting, if we find that the limit of the sequence is not equal to zero, we know that for sure that the corresponding series is divergent. But if we end up finding out that the limit of the sequence is zero, then we don't know anything about the convergence, obviously. That's what we were just saying, but neither about the divergence, right? Because it still could be divergent. Just because, even though the limit is equal to, of the sequence is equal to zero, it still could be divergent, like the harmonic series. So we don't know anything about the convergence or the divergence, right? Okay, if the series, this series and this series represented by these two sequence formulas are convergent series, then so are the series with a constant out front of the a sub n, and you're summing the two series. Okay, yeah, so this is interesting as well. This isn't about properties of summations. Okay, in the algebra videos, I included those videos in this playlist. We go into properties of summations. This isn't about properties of summations. What they're saying here is that if you have two separate convergent series, okay, and then if you take those series and you multiply like you could think about multiplying every term of the sequence by a constant, any constant, which is, you can look at it this way, right? That this c times a sub n, you're multiplying every single term by a constant. Then this series is also going to be convergent. And then by the summation properties, you could do this no matter what. Even if you had a non-convergent series, it's not like if you had like an arithmetic sequence. Let's say a sub n was an arithmetic sequence. We know that series doesn't converge, but you could still multiply an arithmetic sequence by c and then take it out the sum like this, right? So they are kind of given a summation property here, but they're saying though that this sum of the c times a sub n is convergent, since just the sum of the a sub n is convergent. And then if you add the two convergent sequences like this in a summation, that this series is also convergent. And if you subtract them, this series is also convergent. And then they give the corresponding summation properties. Okay, here they give the proof of where these convergence properties come from. Okay, here, this is just an example where when you apply the sum to each of these two, you get, here's a geometric sequence or a geometric series, and then this is that same type of series that they did partial fractions on. So like they apply two different methods and then add up those sums. Okay, and then it ends with a note here. And so this is saying that a finite number of terms doesn't affect the convergence or divergence of a series. For instance, suppose that we were able to show that the series, and here's this series, it starts at n is equal to 4. If we show that that's convergent, but then if you started it at 1, it's not like the formula for the nth term of the sequence changes, right? It's the same formula. But what they're showing here is that they put the first three terms, and then what do you have? That you show that this was convergent. And so the entire series is definitely convergent, because if this is convergent, then that means it converges to a number, right? A actual number. Well, when you add this plus this to that number, you know you're going to get another number. And so that's what, if you can show that any series is convergent, no matter where you start. I mean, even if you could start at -10 or you start at 50, it doesn't matter. If you show that going off to infinity, it converges, then you don't have to worry about, well, will it converge if I started at 1 or 0 or -20? Now it's not saying that, it's not telling you how to get you have to do some analysis to get the value that it converges to, like, right? Like, if you wanted to, you found out this converges to a value, and you wanted to find out starting at 1 this is starting at 1, well, then you have to kind of do some analysis here, get the first three terms and add it to that. So if you wanted to see if it started at -20, you'd have to kind of find those terms from -20 to whatever point you need. But they're just saying that as far as convergence, you don't worry about it. It's going to be convergent. They're just talking about convergence. If you show that any sequence that's turned into a series is convergent, like the corresponding infinite series is convergent, it doesn't matter where you start. If you started at n is equal to 500, then any sequence starting anywhere else is going to be convergent. And you can think about that. Makes complete intuitive sense. Okay, so now let's work some example problems.